The moon, from its dazzling full moon to its crescent form, has been an object of fascination throughout human history. It is Earth's only natural satellite, orbiting at a distance of about 385,000 kilometers. For centuries, the moon has captivated our imagination, but now, scientists say that it might actually be much older than previously believed. Recent discoveries have unlocked new details about its age, challenging long-held assumptions. The moon is not 4.3 billion years old as was once thought. Instead, it is at least 4.51 billion years old, and it could even be slightly older. This revelation shakes up much of what we know about the moon's formation. Despite the centuries of myths, legends, and scientific curiosity, one mystery remains. How old is the moon? Until recently, scientists believed the moon's age to be around 4.35 billion years old. However, recent discoveries suggest it might be up to 200 million years older. The discovery of zircon crystals on the moon, dated to 4.51 billion years, challenges everything we knew about our lunar neighbor. Let's delve into why this discovery is so important. Zircon crystals are like tiny time capsules that trap uranium but not lead. Over billions of years, uranium decays into lead at a known rate, so by measuring the ratio of uranium to lead, scientists can determine the age of these crystals. These tiny crystals, found in lunar rocks, are incredibly resistant to heat, making them perfect for dating ancient rocks like those found on the moon. These crystals indicate that the moon may have been around much earlier than we thought, possibly altering our understanding of its history. This discovery challenges the giant impact hypothesis, which has shaped our understanding of the moon's formation for decades. According to this theory, Earth collided with a smaller planet-sized body, often referred to as Theia, around 4.5 billion years ago. The collision sent debris into orbit around Earth, and this debris eventually coalesced to form the moon. The isotopic similarities between lunar rocks and Earth's composition provided strong evidence supporting this theory, and the rocks returned by Apollo astronauts, dated to about 4.35 billion years, confirmed it. However, with the new discovery of ancient zircon crystals on the moon, scientists are now questioning if the moon might be older than previously thought. The presence of these crystals raises the possibility that the moon's history is far more complex than we imagined. If the moon is older than previously believed, it opens up new questions. Could the moon and Earth have formed together from the same material? One possible explanation is the co-formation hypothesis, which suggests that Earth and the moon could have formed from the same cloud of dust and gas in the early solar system, rather than from debris resulting from a violent collision. This theory posits that instead of a dramatic impact, Earth and the moon might have emerged together over time. This possibility, though intriguing, raises further questions. If the moon and Earth did indeed form from the same material, why does the moon have a surface with less iron than Earth? The giant impact hypothesis explained the moon's iron deficiency by suggesting that the collision with Theia caused the moon to lose much of its heavier elements. However, if the moon and Earth formed together, why would the moon have a different composition? This is where things get complicated. Some researchers propose that after the moon's formation, it underwent a period of resurfacing. During this resurfacing event, tidal forces from Earth caused the moon's surface to melt and reform. This resurfacing could have taken place about 100 to 200 million years after the moon's initial formation and could help explain the age discrepancy between the older zircon crystals and the younger lunar rocks. The resurfacing theory also helps explain the lack of iron on the moon's surface. As the moon's surface melted, heavier elements like iron may have sunk into the interior, leaving behind a crust lower in iron compared to Earth. This provides a potential solution to one of the biggest puzzles in lunar geology. Essentially, the moon's surface could have reshaped, like a volcanic eruption where molten rock rises to the surface, allowing heavier elements to sink as it cooled. The result is a moon with a surface composition that differs from Earth, but a fascinating geological history. If the moon didn't form from a giant impact but instead formed from the same material as Earth, what does this mean for our understanding of the solar system's formation? This shift in our understanding could have real-world implications for how we study other moons and planets. If Earth and the moon were formed from the same material, it suggests that moons around other planets might have formed in a similar way. This discovery challenges scientists to reconsider the processes by which moons form, possibly leading to new ways of exploring moons beyond our own. This shift in understanding also affects how we search for life on exoplanets. If moons around other planets formed like Earth and the Moon, we might need to rethink how we study their atmospheres, surfaces, and potential for life. A moon as old as Earth, potentially formed alongside it, could provide insights into the early conditions of our planet and reveal the types of environments that may exist elsewhere in the universe. In conclusion, the discovery of older zircon crystals on the Moon has shaken our understanding of its history. It suggests that the Moon may be older than we thought and might have formed alongside Earth rather than as a result of a giant impact. The resurfacing theory helps explain the age discrepancy between the older zircon crystals and the younger lunar rocks, offering a resolution to the mystery. While this discovery challenges the giant impact hypothesis, the mystery of the Moon's formation is far from solved. There is still much to uncover, and more surprises may lie ahead. This discovery will undoubtedly shape the next chapter in lunar research and provide new insights into the early solar system and beyond. As we continue to explore the Moon and space, one thing is certain. The more we learn, the more we realize how much there is still to discover. Stay tuned for future revelations as we uncover the secrets of our universe. As we continue to explore the Moon, new data is transforming the way we view our celestial neighbor. These advancements are not only enhancing our knowledge of lunar geology, but are also shedding light on the broader processes that govern planetary formation across the universe. The lunar surface, which has remained relatively unchanged for billions of years, offers a unique glimpse into the past, providing clues about the early conditions of Earth and the formation of our solar system. One of the most groundbreaking methods used in lunar exploration is remote sensing, which allows scientists to gather information without physically being on the Moon. This approach has evolved significantly in recent years, with advanced satellites and robotic missions providing more precise data than ever before. Instruments such as spectrometers, which analyze light reflected off the lunar surface, and radar systems that can peer beneath the surface, have revealed hidden layers of lunar history that were previously inaccessible. The recent discovery of ancient zircon crystals is not the only remarkable find that is reshaping our understanding of the Moon. Researchers have also identified signs of volcanic activity on the Moon, revealing that it was once a much more geologically active world. These volcanic traces suggest that the Moon experienced an extended period of intense activity after its formation, possibly for several 100 million years. This volcanic history is crucial to understanding the Moon's early environment and its evolving surface composition. In particular, the identification of volcanic plains, or lunar maria, has added another layer of complexity to our theories about the Moon's formation. These vast, dark plains were once thought to be the result of meteorite impacts, but recent findings show that much of the material in these regions likely came from volcanic eruptions. The lava that flowed from these eruptions would have cooled to form the familiar basalts that are found in lunar rock samples. This new understanding of volcanic processes on the Moon offers important insights into the Moon's internal structure and the processes that shaped its surface. Furthermore, studies of the Moon's gravitational field have revealed that the Moon's interior is not as uniform as previously believed. While it was once thought that the Moon's interior was relatively simple, scientists have now discovered variations in its composition. These findings suggest that the Moon's interior may contain pockets of material that have a different density, possibly indicating the presence of mineral deposits or remnants of ancient volcanic activity. This deeper look into the Moon's interior could eventually provide valuable information about the composition of other moons and planets in our solar system. In the context of planetary formation, the Moon's history is also raising questions about the role of large-scale impacts in shaping planetary systems. The giant impact hypothesis, which remains the leading theory for the Moon's origin, posits that a Mars-sized body collided with early Earth, throwing debris into space that eventually coalesced to form the Moon. However, as we uncover more details about the Moon's geological past, it becomes clear that impacts alone cannot fully explain its current state. The volcanic activity, resurfacing processes, and complex interior structure suggest that there may have been a combination of factors at play, including internal processes and interactions with the early solar environment. These discoveries are not only impacting our understanding of the moon but are also influencing the way we think about other moons and planets. For example, the study of volcanic activity on the moon has sparked new interest in the possibility of volcanic activity on other celestial bodies, such as Mars and the moons of Jupiter and Saturn. If the moon experienced volcanic eruptions, it's plausible that other planets and moons in our solar system also went through similar processes in their early history. This could open up entirely new avenues of exploration and discovery. In particular, moons like Europa and Enceladus, which orbit Jupiter and Saturn respectively, are of great interest to scientists due to the potential for subsurface oceans beneath their icy crusts. These moons are thought to harbor the ingredients for life, and studying the geological history of the moon could provide valuable insights into the types of environments that might support life elsewhere in the solar system. If volcanic activity played a role in shaping the moon's surface, it's possible that similar processes could occur on these distant moons, providing energy and warmth that might sustain microbial life beneath their icy exteriors. The discovery of older zircon crystals on the moon also has implications for how we search for life beyond Earth. The formation of the moon, and its potential co-formation with Earth, could offer clues about how planetary systems evolve. If the moon formed alongside Earth, it suggests that moons around other planets could have followed a similar formation process, possibly resulting in environments that support life. This raises the question of whether moons around other exoplanets could have habitable conditions, or if they might even have the same geological features that we find on the moon. In the search for life beyond our solar system, exoplanets that are located in the habitable zone, the region around a star where liquid water could exist, are prime targets for study. However, as researchers continue to gather data on these planets, it's becoming clear that moons could also be an important factor in determining whether life could thrive in distant star systems. The moon's role in supporting life on Earth might be more significant than we previously realized. Not only does it stabilize Earth's axial tilt, which has a profound impact on our climate, but it could also play a role in the chemistry of life itself, perhaps offering a unique environment for the emergence of life forms. The study of the moon's surface composition is also contributing to a broader understanding of planetary chemistry. Scientists have long been intrigued by the moon's relative lack of volatiles, such as water and carbon dioxide, which are common on Earth. This difference in composition offers valuable insights into the conditions that prevailed in the early solar system. The processes that led to the depletion of volatiles on the moon could have been influenced by solar radiation, the impact of meteoroids, and the cooling of the moon's surface over time. Understanding these processes may help us better understand the early environments of other planets and moons in our solar system. As the study of the moon advances, new technologies are allowing scientists to gain deeper insights into the processes that shaped the lunar surface. The use of robotic missions, such as NASA's Artemis program, promises to send astronauts back to the moon in the coming years. These missions will not only provide new geological samples but will also test new technologies that could be used to explore other planets and moons in the future. One of the key objectives of the Artemis program is to establish a sustainable human presence on the moon, which will serve as a stepping stone for future missions to Mars and beyond. In addition to its scientific importance, the moon continues to captivate humanity's imagination and inspire generations of explorers and dreamers. As we explore the lunar surface and unlock its secrets, we are not only expanding our understanding of the moon itself, but also gaining new perspectives on the origins and evolution of our solar system. Each new discovery on the moon is another piece of the puzzle, bringing us closer to understanding the history of Earth and the broader cosmos. In conclusion, the study of the moon is far from over, and as our technological capabilities continue to grow, so too will our understanding of this ancient world. From the discovery of ancient zircon crystals to the investigation of volcanic activity and resurfacing processes, new insights into the moon's past are reshaping our view of the solar system. The mysteries of the moon's formation and its geological history are only beginning to be uncovered, and these revelations will likely have profound implications for our understanding of the universe and our place within it.